So what did we get? How much is she investing in her principal? Yeah, 2750. Or wait, is it 2759?
Yes.
Okay. And then the interest rate was
2%.
and then she's doing it compounded quarterly. So N is 4. And so that's 4 times how many years? 4 years? Yeah, so there we go. What is it, 4 years? Yeah, for 4 years. So that's going to be the total amount of money in her bank account. And then they want to know how much interest will there be. So what again would you do?
Subtract it.
You would just subtract out the principal from that answer, and that would be the amount of interest. So definitely some of the questions on the test will be, what's the total amount versus what's the amount of interest? So you either give the total amount or you subtract out the principal and give the amount of interest. Okay, Nora Ortega. No, Ortega. It's not Ortega, it's Ortega. Her savings account has a balance of $20.72. After 8 years, what will the amount of interest be? Well, that's the same question, right? What does semi-annually mean? Yeah, 2 times. Okay. You do that problem, but let's keep going. Make sure you finish it for homework. But let's keep going here. Okay, Barbara, number 27. Barbara knows that she'll need to buy a new car in 2 years. And the cost of the car will be $15,000. Wow, can you even get a new car for $15,000? No. That'd be pretty challenging these days. How much should she invest now at 5% compounded quarterly so that she'll have enough to buy a new car? So this is a great idea. She's saying, hey, I need the $15,000 for a car. So if I just invest some money today, then that money will naturally grow over time, and then I'll have my $15,000. So when we write, and it is compounded quarterly, so again we say A equals P 1 plus R over N. And so what's all of our information? We know that T is 2. And we know that the car will cost $15,000 by then. Where does the $15,000 go?
A.
Yeah, this time the $15,000 goes on A because remember that's the future and P is now. So she wants to have $15,000. And we want to know how much should she invest now. So that's why P is our variable. And then it's 1 plus 0.05 over compounded quarterly and the N T. There. So now we just solve for P. So folks, my recommendation for you when you do this all on your calculator, always work from the inside out. Always work from the inside out. In fact, what I do is I do 0.05 divided by 4 first. Then I add the 1. Then I do the exponent, power of 8. Then I have a number. So I've got 15,000 equals P times a number bigger than 1. Remember we said that this should be a number bigger than 1. And it is just barely a number bigger than 1. So then you just divide it off and you have your P. Now keep in mind, you want to keep as many decimals as possible. I'll just share with you one clever trick you can do. We know that we have to do 15,000 divided by 1.01, all that. But that number's already on my calculator because I just did it. So instead I can do 1.04 divided by 15,000. And I know that's dividing in the wrong order. But if you divide it by the 15,000, then you can put your X inverse button. Remember X inverse was your inverse for your matrices? Inverse will simply do 1 divided by that number, and then it will give you the correct answer. Yeah, that's just what I like to do. So the answer then is 13,580.98. So is Barbara, doing herself any favors? Well, sure. All she has to do is invest $13,580 now, and that will allow her to buy a $15,000 car in 2 years from now. And how much free money is she getting? About $1,400. So if she invests $1,350 now, she's going to have $15,000 later. Nice. Yeah. Much like how all of us are going to save for retirement now. That way all that money will be growing interest, and by the time you retire when you're 65 or 70 or 75 or 80, all that money will just be waiting for you. Yeah. Okay. Number 28 is just like 27. So if you just want to draw a little arrow, say it's just like it, you can do that one on your own for practice. Or would you like it better if I said cross it out? Cross it out. Okay, cross it out.
That was so
Good job, Simone. That's good practice for you, Simone. 28. Well, I don't know. I think so. You're better off having more practice than less.
Or it's extra credit for me.
Hey, it is extra credit in your knowledge. All right. So now we're in a totally new section, 5.2. This is going to take us into these annuities. Okay. Now, what I'm conceptually first. Let's say that you invest. Let's say that you invest $100 every single month. So, and you're going to do it. I mean, it doesn't matter when. We'll just say you invested $100, and we'll say you invested on January 1st. You put $100 in, and then you're going to wait until the end of the year. So here's my number line, and here's January 1st, and we'll just assume it's always the 1st. Here's February, then here's March, then here's April, and then here's May, and June, and July, and August, and September, and October, and November, and December 1st. So then finally we get back to January 1st. So let's just see what would happen to $100 if I invested right now at the beginning of January 1st. Okay? What I want you to know is that by the time it's February 1st, that $100, we're going to compound it monthly. So not only are you investing monthly, you're compounding monthly. This is the idea, that you're investing as frequently as you're compounding. So on the one hand, yeah, your interest is being compounded and the bank is giving you money every time they compound it. But you are also going to go ahead and invest more money every single time as well. And you're going to do it in equal amounts. So we're just going to always invest $100 per month, and we're going to get interest every single month. How much interest should we get? Say 5%? Let's say 5%. So how much is this $100 worth by February 1st? It'll be worth 100 times 1.05. Because that 1.05 is the 5% interest plus 1. Okay, keep in mind the formula, 1 plus R over N. So what we're really saying is that we're getting 5% right here. And in fact, that's what it would look like. If you finish computing it, on the inside there, you'd get like the 1.05 to the 12. So that's 5% per month for 12 times that year. So how much is that $100 worth? That's 100 times 1.05. It's worth now 105 bucks. Now I'm going to let that money invest a whole nother month. So now I'm going to multiply times 1.05 again. So now it's 100 times 1.05 raised to the power of 2. So now that's how much it's worth on March 1st. So then I'm on my calculator, I'm going to multiply times 1.05 again, and now it's worth $110.25. So then what happens? I let the money sit in there, and I'm going to get another 5%. So by April, maybe I'll split that out there. It's going to be 100 times 1.05 to the third power. Because I'm really, now I've multiplied it times 1.05 3 times. Because I've invested it for 1, 2, 3 months. So 100 times 1.05 to the third, I'll multiply times 1.05 again. Now that money is worth $115.76. So do you see what's happening here in terms of the value of my money? How much will it be worth in May? It'll be worth 100 times 1.05 to the fourth. And why to the fourth power? How many months has it sat in there? 1, 2, 3, 4. So by May, the money has been sitting there for 4 months. So that's $100 times 1.05 to the fourth. How much will it be worth by the time we get back to January 1st? So how many months have we let it sit? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that $100, by the time it gets all the way down to January 1st, will be worth 100 times 1.05 to the 12th. It'll be worth $179. Okay, so is that fair? That's just how much that single $100 is going to be worth if you're compounding monthly, and each monthly compounding is 5%. So now here's the big idea. What if I now go ahead and invest a second? So this is one stream of money right here. Now I'm going to invest a new $100 in February. So on February 1st, I'm going to go ahead and drop another $100 in the account. So now how much is that worth 1 month later? 100 times 1.05. And then 1 month later, it'll be worth 100 times 1.05 to the second. And then another month later, it'll be worth 100 times 1.05 to the third. How much will it be worth by the time we get to January 1st? Notice it's only going to be gaining interest 11 months because it didn't gain interest from January. It started in February. So how much will it be worth? Anyone? Not 12 months worth of interest, only 11 months worth of interest. So that was the money I invested in February. What about the $100 I invest in March? Same thing. I invest 100 at the beginning of March. By April 1st, it's now worth 100 times 1.05 to the first because I've had 1 month of interest. And then by May, it'll be worth 100 times 1.05 to the second. So I have 2 months of interest. And how much will it be worth by the time I get to January 1st? Yeah, now it's that 100 only received 10 months of interest. So I'm going to keep this going, okay? I invest $100 in January, $100 in February, $100 in March. I'm going to go all the way down the diagonal here, and I'm going to keep on investing $100 each month all the way up to December. How much will that $100 that I invest in December be worth? Worth? 100. Just 100 times 105 to the first. So if you now look, how many $100 did I put in?
A lot.
I put in $100 on January, February, March, all the way up through December. So how many hundreds is this? 12. I've invested $1,200, and the one that I invested in December is worth the least. It was only worth 100 times 1.05 to the first. The one I invested in November would be 100 times 1.05 to the second, and so on. And then we would just read up the line there and look at all my $100s. All my $100 that I invested and throughout all those months are going to be worth 100 times 1.05 to the first, to the second, to the third, to the fourth, to the fifth, to the 10th, and the 11th, and the 12th. So every single $100 that I invest every single month is all going to earn some interest. Which $100 earns the most interest? Yeah, the one that I invested the longest time ago. And which $100 earned the least interest? Well, the one that I just barely put in December. Okay. So the big question then is, if we do this idea of investing money every single month, then the money you invest the longest time ago earns the most interest, and the money that you invest the most recently only earns a little bit of interest. But what I want to know now is, how much money do I have in the bank? Which is just those totals right there. So how much money? First of all, let's just pretend there was no interest at all. What's the minimum amount of money I should have in my bank if I invested $100 12 times?
1,200.
I should have $1,200, right? I should have $1,200 no matter what, because I just put in 12 $100 bills. However, each one of those hundreds all earned a little bit of interest, some more than others. So what I really want to do now is add up this total. And so I'm going to write down this total right now and show it to you. I'll just write it right here. I'm going to erase it in a second. But my total is going to be 100. I think that pen's. So it's going to be 100 times 1.05 to the first, plus 100 times 1.05 to the second, plus 100 times 1.05 to the third, and so on, all the way up to 100 times 1.05 to the 12th. How do we add that up? Other than painstakingly. Right, we could painstakingly type all of those into our calculator. What else could we do to be clever? What's one thing we could do about the fact that they all have 100 in them? Could we factor the 100 out? So I'll just factor the 100 out in front of the whole thing. And then all I really have to do is figure out what's 1.05 to the first plus 1.05 to the second plus 1.05 to the third, all the way up to 1.05 to the 12th. There, does that make the calculation a little easier to pull out the 100? It's a little better. What, Josue, you say no? Okay. Well, the good news is, folks, that there is actually a formula for finding the sum of a sequence like this. This is called a geometric sequence, when you take a number and you just start multiplying it over and over and over again. So here's a simple geometric sequence. I'm just going to start with 1 and start multiplying by 2. So 1 times 2 is 2, and then times 2 again is 4, times 2 again is 8, times 2 again is 16, times 2 again is 32. That's a geometric sequence because you're multiplying over and over again. It's a geometric sequence. The common ratio in this case is 2. Now up here, I start with the number 1.05, and then I start multiplying times 1.05 over and over again. So now it's 1.05 squared, and then now it's 1.05 cubed, and all the way up to wherever I ended, 1.05. Well, so now in this case, my common ratio is 1.05. Okay? So this is what we're going to be talking about for the whole rest of the section, is a geometric sequence where you multiply by the same number over and over and over again. And what is this number that we're multiplying by over and over and over again? This is the periodic interest rate. It's the interest rate for the period where you invested the money, the period where you're investing more money every single time. Okay, well, it still begs the question, how do we add this thing up? So I'm going to leave that for now, and then we can go back to our notes, figure out some formulas, and then we can come back and figure out how much money we'll have at the end. Alrighty? Yeah, sure, that sounds great. Okay. So everybody, starting with number 29. It says, find the indicated term of the geometric sequence. So what they're saying is that the first term is 3. And then they're saying, so A equals the first term. If you want to write that down, you could. That's the first term. A is the first term. And then R is the rate that you're multiplying by over and over again. Not an interest rate, just a rate. That's the rate of multiplication. So I'm going to multiply times 4. So 3 times 4 is 12. Multiply by 4 again is 48. Multiply by 4 again, that's 192. Multiply by 4 again, and that would be something. Not sure. So, everybody grab your calculator. Type 3, enter. Just type 3, enter. And then hit times 4, enter. And then right now you can just start hitting enter, 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 and then we'll keep on multiplying by 4. So try that out. You should get the sequence 3, 12, 48, 192, 768, 3072, 12, no, 12288, 491 by 2, 196608. And how many terms do we want? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, good. Find the 9th term. The 9th term is 196,690. Did everyone see how to do that on your calculator? You just hit enter the first number, hit enter, and then hit times 4, enter, and you just keep doing that. Simone.
I have a question. Isn't it like another way to do it? Isn't it like when you have to put the little Z or E, whatever?
Well,
and
it's not E, but here I'm going to show you. The actual formula is, first of all, we denote these terms by subscript. So this is A sub 1, this is A sub 2, this is A sub 3, this is A sub 4. We use A to represent terms of the sequence. So this is A sub 5 all the way up to A sub 9. So that's our 9th term. Again, we use the letter A to represent terms in the sequence. So if you want the nth term in the sequence, you take the first term in the sequence and you multiply it by the rate, all raised to the power of n minus 1. Is this what you were thinking, Simone? Yes.
but isn't it another one that's like, it's like the E and then you got n minus 1 at the top?
Yeah. We'll get to that one.
Oh, okay.
So now if I want the 9th term, I would say take the first term, multiply it by R, 9 minus 1, 8 times. So this is the 9th term. I should get that answer. And so A1 is 3 times R, that's 4 to the 8th power. And now everybody, if you type into your calculator 3 times 4 to the 8th, you'll get the exact same answer of 196,000. So you don't have to sit there and hit enter, 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 enter. Although the enter, enter, enter method is clever and fun. But this method will just give you the answer. So for instance, looking at the next problem, we have the first term is 3, and then you're going to multiply by -3 over and over and over. So thinking from the beginning, the first term is 3, times -3 is -9, times -3 is positive 27, times -3 is -81, times -3 is positive 243, and so on. So I could just sit there and start multiplying times -3 over and over and over.
I don't have that one.
You don't?
Mm-hmm.
Oh, what do I have next?
We have the fractions.
Oh, the fraction ones? Okay, well, just as well. So on this one, we've got the first term is a 4th, and then I'm going to start multiplying by a 3rd. So a 4th times a 3rd is a 12th. And then if I multiply times 3 again, 1/3, so times 1/3, that'll give me 1/36. And then times a 3rd again, I'm going to multiply the denominator by 3 again. So it'd be 108, yeah, and so on. So that's just doing it by brute force, multiplying over and over again. But again, there's a formula. So the 6th term, you'd say, I want the 6th term, that's equal to the first term, times the rate to the n minus 1, which is 5. So that's what the formula would give us. And that means our sixth term should be 1/4 times 1/3 to the fifth. And then you can type that into your calculator and it would tell you the answer. So parenthesis 1/4 times parenthesis 1/3 to the power of 5. It gives you some terrible decimal, and then you hit math frac, and it gives you 1/972, which I was almost there. If I just kept doing the pattern I was already doing, the next term was 1/324, and then the term after that was 1/972. Okay, well the key is that we're looking at this idea of multiplying by a number over and over and over again. So the first skill you need is just to understand how to multiply by the same number over and over again, and how to use this simple formula to calculate any given term in the sequence. But that's not even the skill we're going to use. This is just to introduce the idea of finding the sum of a geometric sequence. So what we really want to do is find the sum. Now, I'm suddenly worried that what I have on the board is not what you have on paper. Do you have number 32?
Yes.
Is it actually called 32?
31 for us.
Oh, darn it. Okay, well, everyone look at the problem that says 3 and r equals 2. Now, let's just say that you wanted to find the sum of the first 5 terms. This is doable. You could do this by brute force. You could say, first term is 3, then times 2, times 2, times 2, times 2, and then you can just bust out your calculator, and you can just add 3 plus 6 plus 12 plus 24 plus 48, and the sum of the. So that's pretty straightforward procedure, but we don't want to do that. We want to use a formula. And so, I'm going to erase the work over here.
Are you gonna put all this form like the plus everyone in now?
Wait, what?
Are you gonna give it to us on the test?
The formula?
Like, yeah, that was funny now.
Yeah, well, we're just kind of generating ideas right now, which are going to lead to those 3 formulas. Yeah, like, I mean, we can just skip all this and just start using the formulas. But I want you to have an understanding and a knowledge of where these formulas came from. Okay, so folks, everybody take a look here at what I'm about to do. This is, and in fact, I want you to write this down. Hey, how you doing?
Good, I just wanted to give this to you.
Okay, well, that's wonderful. But let's keep going. That's wonderful. Okay, let's keep going, folks. Everyone write this down. Let's say that I wanted to find the sum of 1 plus x squared plus x cubed plus x to the 4th. And I want to know what that adds up to, because I want to show you this clever trick. This is the clever trick that mathematicians use to figure out what if you add up a sequence of numbers that are all a geometric sequence, meaning I took this, I multiplied times x, I multiplied times x again, I multiplied times x again. So we want to know what that adds up to. So here's the clever trick, everybody. You take both sides of the equation and you multiply it by x. So I'm going to multiply, I'm going to go above it, okay? Multiply this whole equation. Now I have x times s equals 1 times x is x times x is x squared times x is x cubed, and x cubed times x is x to the 4th, and x to the 4th times x is x to the 5th. So you see what I did? I took the exact same equation, multiplied both sides by x, and I wrote it on top of it. And now I have 2 equations stacked on top of each other. Keep in mind, my goal is to solve for s. My goal is to solve for s, which represents the sum of the terms. So now what we do is we simply subtract these 2 equations. So on the left-hand side, I have x times s minus s. And on the right-hand side, what happens if I subtract? You'll notice that for each term I have on top, I usually have one on the bottom. So if it wouldn't do us any good to subtract straight down, because x minus 1, I don't know what that is, but x minus x cancels out. X squared minus x squared cancels out. X cubed minus x cubed cancels out. X to the 4th minus x to the 4th cancels out. And all I have left is x to the 5th minus 1. So now I have x to the 5th minus 1. So you notice that however many terms we had originally started with in that sequence, we're now down to just 2 terms. And now if I factor out the s, so that becomes x minus 1 equals x to the 5th minus 1. I can now solve for s by dividing that term over and I get S is x to the 5th minus 1 all over x minus 1. That's a considerable savings in terms of figuring out what the sum of a sequence is. Okay, well, whether you're impressed or not, here's the rule, okay? So find the sum of 1 plus x plus dot, 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 plus x to the n. Everybody write that down. If I want to know what all that adds up to, the sum is equal to x to the n plus 1 minus 1 all over x minus 1. That's what we learned from this formula over here, because we were originally just going up to x to the power of 4, and the formula was x to the power of 5 minus 1 all over x minus 1. Now, what I really want you all to see is what we've been talking about for x is we're saying that that's actually 1.05, which is whatever interest rate we're going to multiply over and over again. So what we could really do here is say that this number that we're going to multiply over and over again is really 1 plus I, where 1 is the 1 and then I is your interest rate for the period. And now if I take this formula and I put in 1 plus I, so that's 1 plus I to the n plus 1 minus 1 all over 1 plus I minus 1. What do we end up with? We have 1 plus I to the n plus 1 minus 1 all over, the ones cancel, I. I did all of that just to point out to you, do you see this over there somewhere? That's just our formula for future annuity due. So that's kind of it. Okay, I wanted you to have some sort of justifiable belief in where these formulas came from. And the formulas came from the idea of adding up a geometric sequence, which by doing that little trick over there, we were able to come up with a formula, and the number we're multiplying by over and over again is 1 plus the interest. These formulas over here. So that's it. I just wanted you to believe it. That yeah, these formulas come from a natural idea of adding up a geometric sequence. So what do you say? Now we can just use the formulas? Everyone okay with that? I would feel really guilty and sinful if I just said, here are the formulas. So that's why we just did this little exercise. So in that case, though, we can go ahead and cut out these problems right here, because we don't need to go all the way down to this abstract level and actually practice it. What we really want to do is apply all this to finance. So now that we've seen that we're talking about these questions, now we can go back and answer the question about how much money you have at the end of 12 months. So remember that I had 100 times 1.05 to the first plus 1.05 to the second plus plus 1.05 to the 12th. And I wanted to know what all that added up to. See, we could now figure out this formula. And then we could, use the formula and add it all up. Okay. I can tell that you're all very whelmed. Wait, overwhelmed? Wait, underwhelmed? No, just whelmed. Okay, so everyone, you crossed out those problems? The rest of these geometric sequence ones, you can just cross them out. They won't be on the homework. And so now let's go ahead and see how all this applies to money. My focus is to make sure that we all understand what we're actually doing. So it says find the future value of the ordinary annuity. Interest is compounded annually unless otherwise indicated. No, that's what we're actually doing. So sorry, folks, we're all on now number 35. The numbers are different. I'm very sad about this. I don't know why my numbers are different, but the problem should be the same. Is everyone looking at the problem with $100, 0.1 and 6?
Yeah, the ones you said to cross out, we don't have.
Oh, they're not even there? Oh, well, I must have had some part of myself that was like, oh, we don't have to do that. Okay, so everybody, we're on this problem. And the number is 33. Okay, 33. I'll try to cross them out as I can. So that's 34. Okay, so find the future value of the ordinary annuity. Interest is compounded annually unless otherwise noted. So first of all, the word annuity everyone, you should write this down in your own notes. Annuity means that you're going to invest money over and over every time your interest gets compounded. So you're doing the two things simultaneously. So whenever your interest is going to get compounded, you're going to invest more money. So annuity means you invest regularly. So it's not just like some sort of one-time investment. You're doing it regularly. How regularly? As regularly as you're getting your interest compounded. So the two things happen at the same time. And in fact, in an ordinary annuity, it means that you do it all at the end of the month. So what's going to happen is at the end of every single month, they're going to compute your compounding, they're going to compute your interest and give it to you, and you're going to slip more money into the bank. So at the end of each month, they give you interest, and you invest more money. So can everyone imagine that that's just a habit that you have? Like say this is February, so at the end of February, they're going to give you a little interest and you're going to put some more money in the bank. And then at the end of March, they're going to give you a little more interest and you're going to put more money in the bank. Okay, so let's try it. In each of these formulas, we're dealing with the letter I and the letter N. So you should go ahead and write down that I is the rate per period. Period means the chunk of time that you're actually compounding every so often. And N, in this case, refers to the total number of periods. Notice here that this is very vastly different from the N that we had over here. Over here, N was the number of compoundings per year. And R was the rate for the year. Okay? Because we're about to use letters in a different way. So over here, with the compound interest formula, N is the total number of compoundings you get per year, so like monthly would be 12 times per year. And R was the interest rate for the whole year. So if you wanted to find out the interest rate per period, that's when you would do R over N. And that's actually what they're now using as the letter I over here. So this is I is your interest rate for the period, and N is the total number of periods. So they're telling us that the interest rate for the period is 0.1, and that we're going to do this 6 times. And they're also telling us that it's annual. So let's go ahead and write down our ordinary annuity formula. It is future value, so the future value of the annuity is R, which stands for repeated investment, or regular investment, or payment. I would call it a repeated payment, or repeated investment, the amount of money that you're putting in every single time, whereas FV is future value of the entire annuity. How much is this whole thing going to be worth later? And so that is going to be 1 plus I to the N minus 1 all over I. And that's the formula for an ordinary annuity. So in this particular case, that would be $100 that you're investing every single time. And then 1 plus 0.1 to the power of 6 minus 1 all over 0.1. Now again, on your calculator, do not type that whole thing in all at once and hit enter. You need to do a little bit at a time. A little bit at a time. You would do 1 plus 0.1, enter. To the power of 6, enter. Minus 1, enter. Divide by 0.1, enter. Times 100, enter. And if you do all that one step at a time, then your future value, you'll see, is $771.05. That's it. Now, it said that n is 6, so it's compounded annually. That's how many times you're going to compound your interest. So how many times did we actually invest $100? So we're going to do this 6 times. First of all, if you invest $100 6 times, how much would you have? 600. So we know that we should automatically have more than 600. But we're saying we end up with 771. So how does that work? Again, if we're going to talk, this is years. So let's invest at the beginning of 2000, and then 2001, and then 2002, and then 2003, all the way up to 2004, 2005, and then 2006. So notice what's going to happen here. So is that 6 years? 1, 2, 3, 4, 5, 6. Yeah, more importantly, the money is going to get compounded at the end. So you start with some seed money there. You put, you're opening the account, so you put $100 in. And then at the end of that year, they're going to give you interest, and you put in another 100. So I want you to notice, is everybody watching? I don't think anybody. Everybody. So you put your $100 in because you open the account, right? But nothing happens in the beginning. At the beginning of the month, nothing happens. You just opened up the account by putting in your first 100. At the end of each month, or at the end of each year, you put in another 100, and you get interest. So I'm going to say plus interest. And then at the end of that year, you put in another 100, and you get interest. And then at the end of that year, you put in another 100, and you get interest. Then at the end of that year, you put in another 100, and you get interest. Then at the end of that year, you put in another 100, and you get interest. And then at the end of that year, you put in 100, and you get a little more interest. So how many times did you actually put in 100? 7. Because you put in some seed money just to open the account. They didn't actually. How many times did you get interest? 6. So overall, then that's the $700 plus the interest that you earned at the end of every month. So that's the 700 plus interest, which is the 771. Yeah, and keep in mind, this $100 earned a lot of interest because that $100 got interest every single year it sat there. This $100 only got a little bit of interest. It only earned interest once, twice, 3 times. This $100 didn't earn any interest because you just threw it in at the very end. Okay, so that's an annuity and how it works. So I'll go ahead and try one more. This time, our future value is equal to the repeated investment. Always write down the formula, 1 plus I to the n minus 1 over I. And so this time you're putting in $1,000, and it's 1 plus 4% to the 14 years. So keep in mind that this is a little weird to think about. Even though you're going to earn interest 14 times, which means you're going to invest $1,000 more dollars 14 more times, you also put the $1,000 in as seed money to begin with. So already times do you put in $1,000? 15. Because you start with the seed money, and then you're going to do it 14 more times. So no matter what, we're expecting this to be at least 1,000 times 15, $15,000. It's got to be at least 15,000 because you put in the seed money, and then 14 more times you're going to earn interest and put in another 1,000. So then when you actually do all of this calculation, sorry, that was 0.04. Again, folks, on your calculator, I'm going to walk you through it. You do 1 plus 0.04, enter, to the power of 14, enter, minus 1, enter, divide by 0.04, enter, times 1,000, and I get 18,291 and 91 cents. Now that result was actually pretty cool because your $15,000 became $18,000. So how much money did you make? You made $3,000 and some change. Is 3,000? Let's just call it $3,300. You just made $3,300. Is that impressive? I mean, it seems nice, but remember that was 14 years. So $3,300 divided by 14 is only $235 a year. Divide by 12, that's only $19 a month. Divide by 30, that's only 65 cents a day. It suddenly becomes a lot less impressive when you think about daily. But then again, if all of you together gave me 65 cents a day, I would take it. right? I mean, hey, you're not going to turn down 65 cents a day if somebody's going to come up and give it to you. Okay, so all of this is an ordinary annuity. And did you take down all the notes? The annuity means that you're investing regularly. You keep on making regular investments, time and time and time again. And the fact that it's ordinary means that it's at the end of the month that simultaneously they compute your interest and you put in more money. And that's when that happens. Okay, let's try one that's a little more complex. Do you guys have these problems?
Yes,
R equals 7,500. What number is this for you?
35.
Oh, 35? Okay, so I'm 2 ahead of you. Everybody, my number is 2 ahead of you. So just look for the, look for the right problem. So here now it's getting a little interesting. So we have R is 7,500. But now they're saying that, I'm going to have to erase this. You all wrote it down. So now they're saying interest is compounded semi-annually for 4 years. So we have to think real carefully here about what my N is and what my I is. So first of all, N is the total number of compoundings. So if they compound semi-annually, how many do you get per year? 2. And they do it for 4 years. So what you're really looking at is 2 times per year times 4 years. That's really 8 total compoundings. So that's what our N represents, is the total number of times they're going to compound your money. Whereas your interest rate, just like before, I is actually, oh, well, that'll be confusing. You take your interest rate and you have to divide it by how many times they're compounding it per year. So you're really going to do 0.074 divided by 2, which is what, 0.037? 0.074 divided by 2. Oops, 0.074. Yeah. So as before, remember that this term over here in our compounded interest formula, R over N, you're dividing the interest rate by how many times you're getting it compounded per year. That's the period rate. And that's what we just calculated. The period rate is actually 0.037. So every half a year, you're actually only earning 0.037. And how many total times is it going to happen? 8. So now we can go ahead and do our future value of our ordinary annuity. Is 1 plus I to the N minus 1 all the time. You have the formula memorized yet? Maybe a few more times. Yeah. So then R is 7,500. And keep in mind, what does that mean? We're putting $7,500 more dollars in every half a year. So every half a year we throw in $7,500. And then the interest rate we're actually getting is 0.037. And we're going to get interest 8 total times from this bank. So as before, we're going to invest $7,500 how many times? I should say how many more times, because you got to open the account with something. So you seed the account with $7,500 first, and then how many more times do you invest? 8. So how many total times? The seed money plus the 8 more times. How many total times are you investing?
8.
9. 9 total times. The seed money and then 8 more times. How many times do you earn interest?
8.
8 times you earn interest. 8 more times you invest money. You start with the 7,500. So really, we should expect how much money? 7,500 times 9. We should expect at least 67,500, because that's just from it. So again, everyone, on your calculator, very carefully, 1.037 to the power of 8 minus 1 divided by 0.037 times 7,500, and I have 68,372.37 cents. Was that a very impressive amount of interest that we earned? No. I mean, just compare. That 67,500, that was my money. I put that 7,500 in 9 times. That got me the 67,500. So that wasn't very much interest. That's only what? That's not even $1,000 worth of interest. Why was it not a lot of interest? Well, because you're only compounding twice a year, and you only did it for 4 years.
It could be good for the other person.
Well, yeah, that's true. Thank you, Luis. It could be. Okay, so let's just set up this next problem, folks. What is our N and what is our I? Because that's our big question. So we're compounding interest quarterly for 16 years. So how many total interest payments are they going to give us? 4 times a year for 16 years. 4 times 16 is 64. So it's a total of 64 interest payments, and that's also a total of 64 more times you're going to invest $2,500. So you invest the $2,500 to start the account, but then you're still going to invest 64 more times, and they're going to pay you interest 64 times. So then what's my actual interest rate? It's 8%, but since it's compounding quarterly, we divide by 4 to get the period interest rate. So 0.08 divided by 4 is 0.02. That's some good conceptual understanding of what's happening here, okay? You start the annuity by putting in $2,500. Then, 64 more times, you're going to invest it, $2,500, 64 more times. And every time you invest more, they're going to pay you 2% interest. And they're going to do that 64 times. So 64 times you get 2% interest, 64 more times, you're going to invest $2,500. Okay, and then you can just plug it all into your formula. Future value is R times 1 plus I to the n minus 1 log I. Everybody, you want to try that on your own calculator and see what you get? And if you have any questions about your calculator, let me come around and help you. Yeah, try that on your calculator. Tyler, you have your calculator? And said you have a calculator? Let me, oh gee, I don't have any extras. Did it work on your calculator, David? Okay, and David, it worked out? What do you think anyway? I don't have your calculator?
No, I forgot it.
Oh, no. And Lucia, try it on your calculator, make sure it works.
Did you get it?
Simone snuck away.
We keep the cheese.
Hey, it worked, okay?
That's just.
All right, so it's 1.02 to the power of 64 minus 1 divided by 0.02. And then, everybody, I want you to notice something. This is really cool. So R is going to be multiplied by, the number inside was 127.57. I don't know if you noticed or stopped your calculation, but that's what we're saying. The future value is R, which is 2,500, times 127.57. Look how cool this is. How many times in your future value, how many 2,500s will you have in your bank account? How many 2,500s will you have in your bank account? 127 of them. And how many of them did you put there? Only 65, right? Because you put 64 more 2,500s in after your initial 2,500. So you put in at 2,500 and then 64. So that's 65 2,500s that you put in, but your future value is actually worth how many 65 or 2,500s? 127. So by getting all this interest that was compounded quarterly, it's the same as if you invested 127 2,500s, as opposed to the fact that you actually only invested 65. Doesn't that sound a whole lot cooler that way? I mean, I would love to have 65 $2,000 bills in my pocket, but I'd rather have 127 2,500 bills in my pocket. So that last number there is kind of interesting because you know how many times you actually invested 2,500, and this is the result of how much money is going to end up in your bank account. That's almost double, right? I mean, when you calculated it, was it double? That's a total of, did everyone get 318,936?
Yes.
Whereas if you just look at 64 plus 1, 65 times 2,500, 65 times 2,500, 500. And how much did you get out? Almost double. So this is a very powerful example of an annuity that by making repeated investments many times a year, even at a fairly low interest rate, well, I mean, 8% is high right now, the annuity is very powerful because you're investing over and over and over again, as opposed to just one lump sum. All right. Okay, so the next one is what, 37? Everyone is at 37? Okay, yes. Sitting on those. We are. So find the periodic payment that will amount to the given sum. Now see, this is what's very interesting. This is about long-term planning, right? This is actually what's helpful is long-term planning. So let's just say that you want to have $63,000. Right? This is like planning for retirement. How much money do you want to have in your bank account by the time you're retired? So let's just say that you wanted $63,000 in your bank account by the time you retire. Then how much do I have to start investing every single month? Right? Is that what they're going to say? Find the periodic payment that will amount to the given sum under the given condition. So I want to end up with $63,000, and I'm only going to invest money once a year, and it's 6%, and the payments are made at the end of each year. So this tells us that it's an ordinary annuity. Notice that the word end of each year, that means it's an ordinary annuity. Just so you know, the ordinary annuity is when you get interest at the end. I'm sorry, when you invest. An annuity due is when you invest money at the beginning of each month. Okay, so what do we all fill in? We have our future value equals R times 1 plus I to the n minus 1 all over I. And in this case, we're saying that we want the future value to be 63,000. And we're solving for R. So let's figure out what I and N are. N, I like to do N first. We're going to do it 12 years, once a year, so N is just 12. And our interest rate is 6%. It's compounded annually, so it is 6%. So we're actually using the numbers they gave us. So now we have 1 plus 0.06 to the 12 minus 1 all over 0.06. So your best practice then would just be to compute that whole number and write it down. So 1.06 to the 12 minus 1 over 0.06. That's 16.8699. And then just divide it off. Now, another way to divide that off is to just type in 63,000 and then hit divide by second answer. If you hit second negative sign, it's going to pull up the answer you just had. That will give you $3,734.45. What was that, 12 years? Yeah. Now notice, this is really exciting. What if you invest $3,700, and then at the end of each next 12 years, you invest that amount again? So first of all, how many total 3,000s do you have? You put in the first one to open the account, and then you did how many more? 12 more, so that's a total of? 13. 13. So we have 13 of those. So let's just imagine, what's 13 times that? That's only $48,000. So that's your money. You put in 13 of those, but how much are you going to end up with? 63,000. And what's the difference? That's your interest. So you earned $14,452 of free money by doing it this way. Because that's your interest. The next problem is the same. They're both under the same subheading, so just try that one yourself. Folks, what would you like to ask? Is everyone okay? Michelle, how are you doing?
Tired.
You're tired? Okay, well, that's understandable. It's the end of a long day. Jacob, how's this? It's great. Oh, okay. Danny, great. Wow, Simone. That's making sense. All right. I mean, really, at this point, we're just implementing a formula, right? The formula is telling us how much money we have at the end or how much we need to invest. Okay, so do number 38 on your own. Circle number 38. You can do one on your own. It works the same way. And let's try. Slightly different. Now they want to know how much interest do you need to go find. So it says here, Find the amount of each payment to be made into the sinking fund, which is another name for it, so that enough will be present to accumulate the following amount. Payments are made at the end of each period. The interest rate. Yeah, so again, find the amount of the payment. Oh, this is the same question. This just means that we're solving for R. Now notice that they called it something else, a sinking fund. What do they mean it's a sinking fund? It just means that you're sinking more money into it. Right? Like every month or every month or every year or whatever, you're going to put more money into it. But otherwise, I think these are the same problem. So I think I'm going to skip some of these, right? Because we don't necessarily have to keep doing more problems of the same. I'm just going to write down the formula with you. Since this is a sinking fund, which is another word for ordinary annuity, because the payments are made at the end of each period, and that's what an ordinary annuity is, then its future value equals R times IDN. So let's get all of our information. Now it's compounded semi-annually. So how many total times are they going to give us money? It's twice a year for 13 years. So 26 is the total number of periods. And then our interest rate is 0.07, but it's semi-annually, so you divide by 2, and you're actually using 0.035. Now keep in mind they're saying, and this time they're saying find the payment. So we're solving for R. It's going to be 1 plus 0.035 to 26 minus 1 over 0.035. And how much money do we want to end up with? 44,000. So again, this is nice long-term planning. You're like, well, 13 years from now, I need $44,000. So how much do I need to invest every so often? So 1.035, 2.6, minus 1.5. Did anyone else get 41.31? And so dividing that off, it's $1,065.12. So that's how much you have to put away every 6 months. Do you feel like you could save $1,000 every 6 months? Let's think about what that looks like. $1,000 over 6 months is really $166 a month, which, well, that's much larger than a cell phone plan for one person anyway, at least I hope. But so that's per month, and then divided by 30, that's $5 a day. So saving $5 a day, which amounts to the $1,000 every 6 months, $5 a day is significant, right? And I don't know if you've heard of this, but this is what people call the latte factor. That a lot of people, every day on their way to work, they get themselves a latte. And a lot of people, a lot of lattes cost $5 a piece. And so if you're spending $5 a day getting yourself a latte on the way to work, you are essentially spending $1,000 or $2,000 for the year on just coffee drinks. And so you could easily redirect all that money into your savings account and just skip the latte and do something else instead. I don't know what that else would look like. Probably wouldn't be as tasty as a latte. It's what? Yeah, get something else. Okay. Well, folks, let's, you can go ahead and cross out number 42 because it works the same way. 40. Yeah, sorry, 40. Yeah, 40. I'm glad you did it. That's such good practice. Okay, next concept. Hey, I'm just going to really quickly now finish up these last couple of concepts, and then we can take our break. So we're starting a new idea now. Now we're talking about the annuity due. Annuity due is a different formula, and it's a different concept. And what happens now is that the interest is made at the beginning of each year. So instead of them paying interest at the beginning. Oh, no, I'm sorry, not interest payments. Your actual investment. You're investing money at the beginning, not the end. Now you might say, what the heck? How is this any different? Because let's say that you were going to make 6 investments. So we're going to do January, February, March, April, May, and June. Is that 1, 2, 3, 4, 5, 6? But 6 more. 1, 2, 3, 4, 5. There's July. So you would expect you're going to do this, the 600 more investments. Like if you were investing at the end of every month, this is what it would look like. So in the month of January, you invested at the end of January. In the month, well, that's the best one to look at. So in the month of January, you're investing at the end of January. And if you invest money at the end of every month, that would be your 600. Except we were talking about the fact that we placed a little seed money there, and that's how we got the extra payment. So that was an ordinary annuity. Whereas now what we're saying is that we are only going to put money in at the beginning of every month. So I'll show that down below. So that means you do it in January, and then in February, beginning of February, beginning of March, beginning of April, beginning of May, beginning of June, but not the last one in July. So now we're investing money at the beginning rather than at the end, and so there's no seed money. So let's try this problem out. We have a new formula now, annuity due, and you'll notice it looks very much like the other one. What's the only difference between this new formula? On the inside of the bracket, what's different?
N plus 1.
Thank you, Diego. It's n plus 1 instead of n. And then what are we doing outside? We're subtracting out one payment, which makes sense because we are, in fact, subtracting out one payment. Because now we're only investing at the beginning, so this idea of seed money is gone, and we're only going to make those 6 payments, and that's it. So this is called annuity due. So let's see how this one works out. We're going to make a payment of $500. That's our repeated payment. And it's 5 years compounded annually. So writing down N is 5 years total, just once a year, so that's 5. And then our interest is 6%, and that's what it is because we're not dividing by anything. So now we have 1 plus 6 to the 5 plus 1 minus 1 all over 26. And then minus out of $500. Now I bet you all feel like you didn't have to write 5 plus 1. You could just write 6. And that's probably true. So this would really look like 1.06 to the 6th minus 1, or 0.06. Then we're subtracting out a 500. So let's see what we end up with. 1.06 times 6 minus 1. 1 by 0.06 times 500. So that's 3487. But then we're subtracting out of $500.
So what if the 500s just cancel each other out or no? Or you can't do it like that?
It doesn't work like that.
Okay.
Because you're taking this 500 and multiplying it by something, and then you're subtracting 500 later.
Okay.
So we end up with 2987. So how do we know that our model is correct? That we only actually put in 5 payments. Because it's just 5 years. I could change this to January, February. There. 1, 2, 3, 4, 5. Yeah, we're just putting in 5 times 500. So if we just put in 5 times 500, that would be $2,500. Right? And so clearly, we made a good amount of interest here. 2,500 of that money, because we're only investing it 5 times now total, is 2,500, and then we got 2987. So we got like $487 of interest. It definitely cannot be the case that we put in 6 500s Because that would have amounted to $3,000. We got less than $3,000, so somehow we would have gotten any interest and they would have taken some money from us. So for sure, our model here is correct. So for annuity due, the idea is that you're investing money at the beginning of the month and nothing happens on that last month. So when you say that you invest 5 times, it's really just 5 times. Whereas with an ordinary annuity, you put in the seed money and then you invest at the end of each month. And so you actually end up with one more investment amount than you think. Well, so what's the difference? I mean, all of these are just different investment strategies that different banks offer. So ultimately, you would just say, hey, do I want to get an ordinary annuity? Simulations and look at each one and see which one you like best. You know, see which one works best for you. Notice that regardless of when you put the money in, whether you put the money in at the beginning or at the end, when are they always paying you? Always at the end. It would make no sense for a bank to give you money up front because they haven't had your money yet. You know, the only reason banks have money to give you money is because they take your money, but for that entire month, they go somewhere else and invest your money to make money. And so then by the end of that month, they just made some money and then they give you some of it. Okay, let's do at least one more problem of an annuity due. Let's skip number 42 and just move on to one of these word problems. Oh, no, these are regular word problems. And you know what? So everyone, just take a look at these. Number 45, it says Bob deposits $5,000 at the end of each year. So we'll just talk about these. Which is this? Ordinary annuity or annuity due? This is an ordinary annuity. So you already know now that this whole problem is supposed to be ordinary annuity. What about this next one? Sandra deposits $3,000 at the end of each semi-annual period. That's also an ordinary annuity. Do you all want to cross those out?
Yeah.
Go ahead and cross those out. But at least note that now you know how to interpret whether it's an ordinary annuity or an annuity due. You can think to yourself, annuity due means it's due at the beginning of the month. Whereas ordinary, it's ordinary to do payments at the end of the month. Okay. Not too overwhelmingly interested in these problems. And I bet you don't mind. I bet you don't mind if I string these a little bit. Is that okay with everyone? Because we've already done a large amount. Wait, what'd you say, Louise? Yeah, certainly. We've already done a lot of various problems about money. Yeah, we can skip those too, folks. Yeah, you can cross those out entirely. You see, what I typically do is I go through and I'm like, oh, all these problems are so great. Those are great. But then I end up gathering way too many problems for all of you. So you can cross out both of those. What was that, 45 and 46?
Yeah, sure.
Okay. Okay, here's a good one. Let's definitely do this. Wait, what?
Somebody asked if they
Somebody asked if they think.
if we can go to break.
Oh, I was just going to skip break today. Well, okay, yeah, go ahead.
We can go at 4:15.
No, let's take a break. So come back at 3:34. Good question. Because, Simone, if it's up to me, I would never take a break. We would just go.
Because math is just that fun. Yeah, math is that fun.
All right, let's take a break.
Somebody asked me.
Trying to keep my A in class.
Yeah.
Yeah. 20 really gets you.
Are you 20 on the dot?
Oh, yeah, well, I turned 21 in October.
Oh, nice.
Oh,
Oh, yeah. You know, this is like, you remember when like part-time comment evening guy, like, does his work after.
Obviously.
Yeah, you're right, and I opened it up. Once it's. It would be nice not to be.
I'm just gonna bring it to you as. I like that, if I work, interested, let me know,
Okay.
and I'll let you.
Mr. G,
Yes.
did anybody take the last practice test or no?
Do I what?
Did anybody take the last practice?
Nobody took either of them. There's still two here. So if you want to take one.
Thank you.
El Chapo.
You think so?
See the missing one? Yeah, since today's alive.
Mental, emotional safety. I actually didn't change much schedule.
Provide.
Yeah.
His wife was like, I never even knew.
I am,
Yeah, so it's
but
like I
I
never
am
knew he
taking
was doing
Walmart.
this.
So. See.
To
I wonder if it's even. I can't sit and read. Like a sentence.
but here, really, it's like,
You just got sentenced to in life. There's no throne.
Maybe we're gonna what I'm good.
Yeah. Look at all the good behavior.
That's stupid. Yeah, I don't really know. Hold on.
Passed away. And he was the only one that had passed away. She's like, "Oh, that's one of the but if you find so that someone to try to
Oh my. All right, let's keep going, folks. Okay, I'm going to dwindle this down to just a couple, 2 or 3 problems of the last 2 concepts, just to see how it works. So, did we finish? Oh, we didn't even do these yet. Okay, let's do this one. Larry, who wants to start an IRA? What is an IRA?
Isn't that?
Which is what? Which is what?
Internal Revenue Service?
Very good, Internal Revenue Service. This is an individual retirement account. So jot that down, individual retirement account. Individual retirement account, meaning this is where you're gonna save all your money so that someday you can retire. So Larry wants to start an individual retirement account as opposed to, say, when you're on a pension plan with your business. Some businesses these days still have a pension plan, meaning so long as you work for them, at the end of your time of service, they're gonna pay you money. So that's pension. Okay, so IRA, they will have $610,000 in it when he retires 30 years from now. So that's what he wants to have at the end. How much should he invest semi-annually in his IRA to do this? if the interest is 5% compound semi-annually. So nowhere in here. If it says nothing, you can assume ordinary. Like this doesn't say end of the month or beginning of the month, but it's an ordinary. So since it's ordinary annuity, you just drop down the formula, future value equals your repeated investment, 1 plus I in the end minus 1 over I. And what do we have? He's investing semi-annually. So that's twice a year for 30 years. So what's N? Twice a year for 30 years, and is 60. And then the interest normally is 5%, but we're splitting that twice per year, so it's 0.05 divided by 2, and so that's 0.02. Okay. So at this point, you just plug it all in. Oh, except one other thing. He's saying that he wants to end up with $610,000. And what we're trying to do is find out how much he needs to save.
So we're finding for R.
Yeah, we're solving for R. Because this is the whole idea that when you do an IRA, typically they do paycheck deductions, meaning you're getting paid through your work, and you go ahead and have some money deducted on a pre-tax basis, and you get to put it in your IRA. So we want to end up with $610,000, and we're asking how much money do you have to actually put into your IRA every single month, or in this case, every 6 months, because it's semi-annual. So 1 plus 0.025 to the 60 minus 1 over 0.025, and then solve for R. 1.025 to the 60 minus 1 divided by 0.025. So I got 610,000 equals R times 135.99. So then I got a payment of 4485. So what we're saying is that Larry wants to retire in 30 years with 610,000, which is a lot of money. That's over $500,000. Then he needs to invest 4,485 every 6 months, which is really what? If that's every 6 months, and you divide by 6, that's really $747 per month. That's a fair amount of money to stick aside and save. Okay, number 50 is, or your number what, 48 is the same question. Joan, she wants to do an IRA. So everyone cross it out. All right. Now this is a new type of problem. So far we've seen ordinary annuities where you invest at the end of the month. You've seen annuity dues where you invest at the beginning of the month. And now we're going to talk about present value. Present value is pretty interesting. Present value is saying, yeah, I can invest a certain amount of money every month to get me to my goal. But why don't we just say, hey, forget doing it every single month. What if I just had one lump sum at the beginning? What's one lump sum at the beginning that would be equal to, doing a bunch of regular investments? So let's see, the present value of the ordinary annuity. So if you're going to make payments of $35,000 made semi-annually for 12 years at 5% compounded semi-annually, so what does that look like? You're going to make this payment twice a year for 12 years. So the question is, instead of doing $35,000 twice a year for 12 years, which is 24 payments of $35,000, why not just do one big lump sum investment once, right now? How much would I have to invest so that that money would have the same amount as those 24 payments? Does the question make sense? So instead of making 24 payments over the next 12 years, let's just do one big investment right now at the beginning that will end up giving me the same amount of interest later on, or the same total amount. So let's try it. That's the present value formula. It's P equals R1 minus 1 plus I to the negative n. We have to be very careful about that negative. And so what we're saying here is, in this scenario, P is the lump sum at the beginning. So that's like if you're like, forget all this regular payment business, I'm just gonna make one big lump sum investment. What one big lump sum investment at the beginning would be equivalent to all of these repeated payments? And keep in mind that you can run the question backwards. What if someone's like, hey, all you need to do is invest $1 million today? And you're like, I don't have $1 million to do it over the next 20 years. So you can run the logic either way. We're just talking about equivalencies. What's equivalent? Okay, so let's try the problem. The payments are $35,000, so that's your R. And we're making them semi-annually for 12 years. So let's keep in mind that N is twice a year for 12 years. That's 24 payments. And the interest rate is 0.05 divided by twice a year. So that's 0.025. And now we can figure out what lump sum would be equivalent to doing a bunch of $35,000 payments. So what do we have then? 1 minus 1 plus 0.025 to the negative 24 all over 0.025. Okay, so folks, on your calculators, notice that when you do the power of negative 24, you better put that negative 24 in parentheses to make sure that your calculator is evaluating that exponent correctly. So everybody try it on your own calculator and see what you get. I'll break it up into 2 smaller calculations. So let's just do everything in there first. So 1.025 to the power of negative 24. 1 minus that number divided by 0.025. And everyone check your own work. I got 17.8849, which is really just 0.885. Now, could you do that whole numerator in one calculation? Yes. You could just type in 1 minus 1.025 to the power of parenthesis negative 24. And then divide that by 0.025, and you'll still get the 17.885. So what is the lump sum? 625,000. If I could just invest this much today, then 12 years later, I'll have the same amount of interest as if I had done 35,000 twice a year for 12 years. Yep, that's what present value is asking. So on your sheet, when you write down present value, you might want to write parenthetically under it lump sum. So whenever we're talking about a lump sum question, we're talking about creating an equivalence between doing a whole bunch of payments for the next few years versus one big payment at the beginning and then just letting it sit. What's that? What's that?
All of negative 24.
Why did I get 24?
No, I mean, can we put in the complement negative 24?
Yeah, you have to. Yeah. Here. So that first the numerator would be 1 minus 1.025 to the power of parenthesis negative 24. That's just the numerator. Okay, and then the next question is similar. They're saying, I'd like to make payments of $62 every quarter for the next 10 years at 4% compounded quarterly. And if I did make $62 payments every quarter for the next 10 years, I would end up with a certain amount of money. And what we're asking is, how big of a lump sum one-time investment would I have to make now such that 10 years from now, I'll have the same amount of money as if I did make the quarterly payments? So that's what we're asking, the present value of an ordinary annuity. So we'll try that one more time. The present value of an ordinary annuity. So 1 minus 1 plus I to the negative n over I, where in this case, n, it's quarterly for 10 years, so 4 times 10 is 40 total times that you're investing 62 And so we end up with the lump sum is equal to the $62 payment that we're making, 1 minus 1.01 to the negative 40 over 0.01. So try that again on your calculator. The numerator itself, 1 minus 1.01 to the power of parenthesis negative 40, then divide by 0.01. I got p equals 62 times 32.835. And times 62, and my lump sum is $2,035. Well, we write out all the decimals. $2,035.75. Okay, well this scenario has numbers that are much easier to grasp. So I still don't know how much money we're going to have at the end because we didn't even calculate that. But whether I do $2,035 today and then just wait 10 years, or $62 per quarter, I'm going to end up with the same amount of money. Which one sounds better to you? Investing $2,035 today and then being done with it, or doing $62 every 3 months? $62 every 3 months? Yeah, not bad. So that's what we're talking about with present value. It's a lump sum. Really, what you could call it is the lump sum equivalent. Lump sum equivalent. Okay, so we did both of those. You can cross out the next two. Your 51 and 52. Because they're the same problems. Okay, now that brings us to amortization. Have any of you heard the word amortization? You have me, Cheryl, in what context? Okay, perfect. Accounting. What were you talking about? Okay, that's fine. So everyone, the word amortization. I think the most exciting way to look at this, because amortization is still just the same formula. All right? Everybody now notice that this is the same formula for amortization if you solve not for the lump sum, but if you solve for the payment. So what we were just doing is finding the lump sum. If you find the payment, that's called amortization. And this makes the most sense about a house. You want to go buy a house. And let's just say that you're going to buy a house and it's $200,000. So that's the lump sum that you're borrowing today. And I want to pay back the $200,000, but instead of paying it back like today, which I can't do because I didn't have the money, I'm going to pay it back a little bit every single month. And that's what you call your mortgage payment. Right? So if you take a loan of $200,000, and that buys your home, and then you're going to pay a mortgage payment. How long do you normally make a mortgage payment? What's the most standard mortgage? How long do you pay off your house? 30 years. Most people do a 30-year loan. So normally when people buy a house, whatever the cost of the house is, they do a mortgage that's 30 years long. Wait, why are you smiling?
That's high.
What's high?
30 years?
But does it seem like a long time?
Yeah.
Yeah, because how long do you normally get to pay off a car? Normally they do that in 10 years, maybe 5 years. But a house is 30 years. Unless you do a shorter mortgage and you can do a 15-year mortgage. That's the two most standard options, 30-year mortgage and a 15-year mortgage. So the question is, if I want to pay back $200,000 over 30 years, then how much do I have to pay every single month? Now what you might think would be obvious is just take $200,000 and divide it by 30 years. And then you know how much you're paying back per year. But that doesn't take into account interest. Right? So it's not a simple calculation. But I want to go ahead and show you an amortization schedule, just in case you've never seen one. It's very surprising. If you go online to your favorite Google, and you do amortization calculator. So here's an amortization calculator. Everyone see that? Well, I'll erase that. Loan type. I'm going to do a home purchase. Credit amount, let's do the $200,000. And loan term is 30 years, and the interest rate, we're gonna just leave it at 5%. And calculate. So what they're saying is that your monthly payment will be $1,073. And you're gonna do that every single month for the next 30 years. That's the amortization amount. So when we say that we amortize the mortgage for the next 30 years. Now you might say, well, gee whiz, if I pay $1,000 for 30 years, that's a total of $386,000 that I just paid for a $200,000 house. And yep, when you do a 30-year mortgage, you end up paying almost double what the house actually cost, because that's the cost of interest. But that's just reality. That's how mortgages work. It's a lot of interest to pay on a $200,000 loan. So does it give it to us? Yeah, here it is. So take a look. Every single month you're paying $1,000, right? Well, most of that is going to pay the interest. Because on a $200,000 loan, that's a lot of interest. So most of the $1,000 goes to paying interest, and only a little teeny bit goes to pay down the principal of the $200,000. So then, though, by the end of the 30 years, so look at us, we're scrolling down 30 years into the future, all these payments you're making. Imagine by the end, there's not that much principal left to pay. You know, now there's only like maybe $13,000 left to pay. That's not a lot of interest. So now your interest payments, if you look right here in January, now your interest payments aren't that much. There's not that much interest you owe on such a low amount of capital or principal. And so most of your payment is paying down the principal. So it's this weird flip-flop where at the end, you're paying very little interest and you're paying a lot towards the principal. Whereas at the beginning of your 30 years, you're paying mostly interest and very little towards your principal. And that's what this graph up here represents. Right here, this is the actual balance. The red line is the balance of the $200,000 that you owe. Whereas the yellow is how much you're paying in interest, and the green is how much you're paying in principal. So it's pretty crazy. In the beginning, most of your money is going to pay the yellow interest. Only slowly are you making larger and larger principal payments, and the red line represents how much left you have to pay towards your mortgage. Okay, well, in any case, that's called an amortization schedule. And amortizing simply means make an equal monthly payment. That at the end of 30 years, everything will be paid off. All the interest will be paid off, all the principal will be paid off, and you're done. So let's do a couple amortization problems. As I said, when you do a lump sum problem, you're solving for P. When you're doing an amortization problem, you're solving for R. So let's try it. Find the payment necessary to amortize the loan. That just means how much do I have to pay monthly? So we're going to take out a loan of $14,000. It doesn't have to be a house. This could be a car or a boat. Why would anyone buy a boat? But maybe someone would. Well, anyway, it's a $14,000 loan. And so we're going to go ahead and write down our lump sum amortization formula. This formula is both lump sum and amortization, depending on how you use it. So we want to take out a loan of $14,000. That's the lump sum. And then we want to solve for R. And let's see. Let's write down our N and I again. N, it's semi-annual. Hold on. It's compounded semi-annual. Oh, but there's 10 semi-annual payments. This is weird the way they're giving it to us. They're straight up telling us the N value. We're making a total of 10 payments. So they're telling us N is 10. That's very different from the previous problems. Normally in the previous problems they say 10 years. But this is saying that we're making 10 payments. And the interest is 7%. Well, it's 0.07, but it's semi-annually. So that one still does get divided by 2. It's a little confusing. When they give us an interest, we still have to pay attention to how much it's compounded. But here they're telling us the N value. Okay, so we have that. So it's 1 minus 1 plus 0.035 to the negative 10, all to the 0.035, all over 0.035. And this is going to help us calculate the amortized payment. So 1 minus 1. I got 14,000 R times 8.3167. Oh, 66 actually. And did anyone else get 1,683?
Yes.
All right. Now, here's the exciting part. That's the amortized payment for a $14,000 loan. Now, how many payments are we going to make? Times 10. How much total money am I paying? I'm paying $16,838. Right? Because if I do that 10 times, I'm paying $16,000. But what was my loan for? $14,000. So you can tell I'm paying back more than what I borrowed, which is normal. If you borrow money, you should expect to pay back more. If you borrow money and give them back what you owed, that better be a friend, right, or a family member. And if you borrow money and you pay them back less,
It's a good friend.
yeah, a really good friend. You should pay them back. Okay, so that's amortization. The next one is just like it. Let's see here. Maybe that'll be the last one we do. Or because I crossed out the next pages. Oh no, you know what? Just go ahead and cross out that one, and let's flip a couple pages. You can cross off all of. You can cross out all of 55 and 56, and you can cross out all of those, the 57 through 60. This right there it says use amortization tables to solve the problem. That just means go look it up somewhere. Okay, this will be our last couple of problems. Your 61 and 62, folks. Are you excited?
Yes.
Are you really excited? This is it. These are our last two.
What about the back page? So we crossed out 66 through 68.
Yeah. This is our last one. All right. So, I can barely read that. Find the monthly house payment necessary to amortize the loan. Okay, well, this is great. I mean, this is a real standard question. Now, are there any houses that you can buy for $60,000?
No.
Maybe not. Maybe not. That'd be rough. Maybe a townhouse. You could get a townhouse or a condo. I bet there are some out there that you can get for $60,000. So let's just consider it, okay? Let's say you want to get a townhouse or a condo, and you take out a 30-year standard mortgage, and you're going to pay 7%, which is astronomically high right now. Most housing rates are like 4% or 5%, but let's just say. So we're going to find the amortization. So we use the lump sum formula. Now, folks, I hope you all know this problem is really interesting. This is really interesting. You're saying, hey, I want to buy that $60,000 townhouse. How much do I have to pay every month? You know, what's my mortgage payment? That's what we're asking. When we talk about amortizing a loan, we mean, what's my mortgage payment? So my $60,000 is the lump that I'm taking as a loan. R is what we're solving for. And now let's see. This is monthly, right? Monthly house payment. So N is 12. So my N, sorry, not this N. N is 12 payments for 30 years. So 12 times 30 is 360 payments. And my I was 0.0729, but we're dividing that by 12 because we're doing it monthly. So whatever that is. Now, this decimal is pretty long, 0.006075. You have to use the whole thing. Don't just go rounding. The bank surely isn't going to round. Because they want all their money.
They'll round up.
Yeah, exactly. They'll round up if you're not careful. So 1 plus 0.006075, all raised to the power of negative 360, all over 0.006075. And again, we're solving for R. So let's see here. 1 minus 1. The power of. Okay, right by 0.1. I got R times 146.0085. And so dividing, I got a monthly payment, oh, this is cool, of $410.
Well, it's not bad.
Well, that's not bad at all. My goodness. I think any one of us, if you could live somewhere for $410 a month, then after 30 years you own the place, I don't care if it is just a 1,000 square foot townhome. That's great. Now let's check. What's 410 times 360 payments? Right? Because you're doing 12 payments a year for 30 years, that's 360 payments. You take that and multiply times 360. How much are you paying back? Oh no.
Triple, quadruple.
Yeah. Boy, that kind of feels like a bummer. The townhouse was $60,000, and how much are you paying off?
More than double.
Yeah, more than double. Now let's go back to how we felt about the 410. Right? 410, we're all like, woo! But now we're like, oh. To do the calculation, because you can see, is a 30-year mortgage ideal? No, it's not ideal. But it makes month to month easy, doesn't it? See, this is why people do a 30-year mortgage, because it makes month to month easy. They're like, hey, no problem. I can handle $410 a month. That's easy. Whereas, you know, the reality of how much you're paying when you're done, you're like, oh man, I really paid back a lot. Whereas if you went to a 15-year loan, how does that change? If we did a 15-year loan instead of, let's look at how the numbers change. Only 15 times 12. So that's 180 payments. And so that's 180 payments. That's all that changes. So we change the number of payments. Did someone already do the calculation? Is that what you just told me, Diego?
Yeah.
Oh, you did that very fast. I'm still up here rambling on. 180 divided by 0.00. Oh, and it's not that bad of a difference. It's now only $549 a month. Is that what you said, Diego?
I can do it.
Oh, you were just, who said what? Oh, okay. All right, so look, folks, this is the difference. This is really helpful. That's the difference between a 30-year loan and a 15-year loan. So if you do a 30-year loan, you're only paying $410 a month, and you're like, oh, that's great, I can handle that. Whereas a 15-year loan, how much more is it? Not terrible. You know, if you're already budgeting $410 for a mortgage payment, could you budget $549 for a mortgage payment? Probably. You feel it a little bit. You're like, oh man, that's 140 bucks that I have to give up. But now look at how much less you're going to pay. Everyone, are you ready for the big payoff here? 549 payments, $549, 12 times a year for 15 years. Look at how much you're paying off now. Are you looking?
No.
98,832. Folks, that was a massive difference. That's a massive difference. What should you do? A 30-year loan or a 15-year loan?
60.
What? A 60-year loan? No. Obviously, you should do a 15-year loan. Obviously, that's what you should do if you can handle that. Because, after all, how much more expensive is the monthly payment? Not a ton. It's a bit. It's enough to be like, oh man, I got to cut back on some of my leisure time activities. But how much less are you paying in mortgage? Almost $50,000. Now, you might say, I'm saving $50,000, right? I'm saving $50,000. But how much did I actually cut? How much did I actually take out here? So if I do 549 minus 410, and then I do that times 12 times, well, what? Oh yeah, just how much extra money you're putting away, and you're only doing it for 15 years. Oh my gosh. It's only actually costing you $2,000. How can that be? If I subtract those two, 549 minus 410, that's per month. times 12 in a month times 15. It's only costing you $25,000. So that extra money that you're paying there to go from 410 to 549, you're paying 25,000 extra. Are you all with me on this?
Yeah.
You're paying 25,000 extra, but look how much you save in interest.
Save double.
Yeah. So, I mean, I hope that I've convinced you all that doing a 15-year loan is really the way to go. It hurts a little bit month to month, but you're going to be so much happier in the long run.
It's like college tuition.
Yeah, exactly. Now, all that said, what do most Americans do?
30.
Yeah, I mean, that's just the standard. Most Americans do that. And who's happy about it?
The bank.
The banks.
Do you have a 15 or 30?
Boy, you're really asking me a personal question.
Oh, is that personal?
My wife and I got a 30-year loan,
Mhm.
but we make extra payments
That's like-
every month.
That's what I was about to say, can't you do?
Yeah, and the extra payments are paying down the principal even faster. And so we're still gonna pay it off before 30 years, but we're getting the best of both years. Wait, are we getting the best of both? I don't know. Maybe we're getting the best of both worlds because we have a lower payment, but we're making extra payments and so we'll pay it off early.
Or you can do your little math technique.
Yeah, I mean, I could just do the math technique. I mean, geez, just do the math. All right, folks, we're done. Right? We're done. Yeah, we crossed out all those problems. There we go. We have it. Now your
Or do we
practice
cross
test.
out 62 and 63 to 65?
Yeah, I say you cross out all the rest. Now, strangely enough, I don't have my practice test up here for us to look at, so I need a moment to email myself the practice test.
You want my paper?
No, I need it up on the screen so we can all look at it.
I'm trying to be nice.
Yeah, thank you though, Simone. That's very kind of you. You mean that extra that I gave you that's mine anyway?
Yeah.
Oh, it's a lot of math. Pretty for a nap.
Yeah, no.
And homework's due tonight.
What's due tonight? Wait, why is homework due tonight? Oh, yeah, right, because today's Tuesday. Yeah, the only due tonight is chapter 4, not chapter 5, right?
But it's just, but 17 is. It's due tomorrow. So yeah.
Yeah. In any case, I'll extend chapter 5 until Thursday. Is everyone happy with that?
Yeah.
I'll extend everything until Thursday.
Perfect.
Okay? Everything's due Thursday.
Cool.
Okay.
Let me pull up my.
You still gonna wait till Thursday.
I'll still probably do Wednesday night, Thursday.
Yeah.
No, I wouldn't do that to you, Mr. G. You help us out.
No, it's not a matter of doing it to me. You do it to yourself. Exactly right. Okay. Now again, I don't think we have to do every single one of these problems, but it wouldn't hurt to do some of them. So is this what everyone has?
Oh, hold on, time out.
There's no timeouts.
Yeah, I still got 2 remaining.
All right. Now, folks, keep in mind, this is your practice test, which means this is what your test looks like. So when you come back to class on Thursday, I sure hope that you already sat down and figured out how to do every single one of these problems. I mean, that's how easy it is. You have all the time in the world right now to figure out how to do these questions, and then on Thursday, you just come in here and you do them. So should we just talk about each one, not necessarily solve the whole thing?
Yeah.
And you can take notes for yourself. So like in number 1, what are we going to do? Yeah, we're just going to graph the feasible region. So in both of these equations, what do you have to do? Yeah, you just solve for y. So you solve for y. So for instance, don't take my word on it, but the first one would be y is greater than or equal to -1/4 x minus 3/4. Again, don't take my word for it. And then the next one would be y is greater than or equal to, just 2x plus, no, -4. Okay, again, I could be wrong about that. I just did that in my head. So what would those look like? One of my lines would look something like this, and the other line would look something like that. This one is shading up, and this one is shading up, and therefore, that's my feasible region. Right? Again, don't sketch what I just wrote, and don't write down those equations. I could be wrong. I could have made mistakes. But that's the end result. Right?
I got a different number.
Yeah, you probably did, because I...
Oh, yes, you have -400.
But I do think those are right. Okay, so that's how you would do number 1. solve them for y, graph them, shade them.
Yeah, that's why I was confused on how we got 3 4s, but we have different numbers.
You do?
Yeah.
Oh my gosh, your numbers are different than mine?
Yes.
Yeah, ours
Your
is
number-
-4, yours is -3.
Oh, yeah.
Oh my god, boy. Hold on. Oh, yours are both -4,
Yeah, and then the bottom for number 2.
Oh, that's totally different. Okay, hold on, folks. I obviously don't want to keep doing this. I want to have the same one. Oh,
That's the test.
folks, that's a great point. That's why that's different, because that's the test. Now that all makes
I
sense.
should have said it.
Let's try it again. Let me get the practice test.
Now we know.
Now you know what to expect for the first 2 problems.
So now we know the first one.
Yeah, that's fine. I don't mind you guys knowing that.
We still get it wrong.
We still can't graph it.
That's fine.
Okay, here we go.
We're just gonna graph it like.
All right, well, this is even better because I'm posting the solutions up here. That way we can just have a conversation about seeing what the work looks like. There we go. Okay, that'll work. So you can see what I did. Nope, this is still not what you guys have in front of you. Wait, no, this is what you have in front of
Oh,
you.
yeah, that's what we have.
Okay, good. All right. So yeah, so you can see that for the first one, I took both inequalities, solved them both for y, and then graphed it and shaped it. Of course, these solutions are online, folks. You can just go to Canvas and go to announcements, and these solutions are online, so you can look at them there. So, you know, I guess the question is, what questions do you want to ask about this process? Yeah, any questions on number 2? Again, you'll notice, what did I do in number 2? What did I write in there?
You just made it a matrix.
Yeah, I just made it a matrix. I added in my variables, my inequality symbol. What was the actual question? It said, use the table to find the system of inequalities that describes the weekly production. So what I'm really asking for here is the system of inequalities. That's the system of inequalities. That describes the weekly production.
Is there a way to graph that in your calculator, or do we just have to do it by hand?
You have to do it by hand.
Okay.
You can graph the lines on your calculator, and then you just make a graph of it.
Okay.
No, your calculator will not do inequalities, it will only do equalities. Okay,
We should make calculators that can do.
that would be cool. It's called
Mine does.
the internet.
Oh, you're
and
using
Louise.
perfect, Louise, aren't you?
Yeah. All right. Oh, it's not gonna work.
Calculators.
There we go. Okay. Number 3, folks. I give you a feasible region, and I ask you to find the maximum and minimum value of the objective function. So remember, the only values that matter are the corner points. So you take each of those corner points. You'll see how I did it. Since the objective function is 9x plus 5y, I wrote down 9 times all the x values plus 5 times all the y values, and then I just read off, each calculator. That's just the way I did it. I mean, ultimately, you just have to plug in each x and y into the 9x plus 5y. Probably a table would make more sense if you had x, y, and then 9x plus 5y. And then you put in all the coordinates. So the coordinates are 2, 0, 0, 3, 0, 5, 10, 5, and 10, 0. And then you're just going to compute all of those. You can probably do a lot of that in your head. 9 times 2 and 5 times 0, so that's 18. And then 9 times 0 and 5 times 3 is 15. And then 9 times 0, 5 times 5 is 25. This one's tricky. 9 times 10 is 90, plus 5 times 5 is 25. 90 plus 25 is 115. And then 9 times 10 is 90, and that's it. So that would be your maximum value, and that would be your minimum value. And that's what I came up with over there. I wrote the coordinates down in a different order, but that's what you're being asked to do. Cool. Okay, and number 4, use graphical methods. So again, we can always pretty much ignore this part, right? The x is greater than 0, the y is greater than 0. That's just saying that we're using the non-negativity assumption, that we're only interested in the first quadrant. and then you have your objective function and your inequalities. So once again, you solve both inequalities for y, graph it, and then shade it.
That's it.
Yeah. So both of these get shaded down, and since they're both being shaded down, that little teeny thing there is my shaded feasible region. And so you can see your corner points. You have those corner points right there. And then you find those corner points, which I wrote them all down here. And then you plug them all into the objective function and see what you get. Any questions about those?
So we have to get like the max, and then when x equals 3 and y equals 2.
Well, in this case, they're just asking for the maximum solution. So you would check all 4 corner points, like I did, and I got all 4 calculations, and then that was my maximum. Okay. All right, moving along here. I crossed out number 5. And so, trusting that I wrote that, I'm going to say you don't have to do that one. So all of you can cross out number 5 as well. How's that? Is that
Why did you cross it out? It was complicated.
You know, why did I cross it out? Because I think there's another problem later on that's going to test the same similar skill. And this one ended up with a bunch of fractions in a very unsavory way. And I felt like sometimes we can get bogged down in details of fractions and decimals, and then I want to focus in on concepts rather than whether or not you all can follow along with decimals and fractions the whole way. Did I answer your question? Okay, so chapter 4. Simone, you had questions about chapter 4?
Yeah.
Okay, so number 4, folks, you can see the first question, introduce the slack variables and write the initial simplex tableau. So, like this first inequality here, you're only introducing the slack variables into the constraints, the inequalities. So we would say 2x1 plus 5x2, and then we add in a slack variable, 1s1, so that it actually equals 8. Not less than or equal to 8, but actually equal to 8. So I added the quantity that boosted this value up to actually equal 8. And then in the second one, we did 3x1 plus 5x2. We don't add that slack variable, but instead we add a different slack variable, s2, so that that equation actually equals 11. So what we end up doing is that we add a slack variable to the first inequality and a slack variable to the second inequality, so that both of those become equalities. And then we have our objective function, which we rewrite with all the terms on the left, so that we can, if we move 4x1 and x2 over to the left, it's negative 4x1 minus 1x2 plus no slack variable plus no slack variable plus, I wrote my 11 too close, plus no z plus 1z. Okay, so folks, in all of these problems, you know that we've set it up in a pretty standard way, where we do our x variables first, and then our slack variables, and then our z variable, and then the number that it's equal to at the very end. So after now that I've written all that, now Simone, do you see what I've done?
Yes.
Okay, is that all okay? Anyone else have any questions about? So that's actually writing 3 equations, but what they really said was write the initial simplex tableau, and that's what this is. So the initial simplex tableau is just all the coefficients of what I just wrote. So you just take all those coefficients, strip away all the variables, and just write down the numbers. Questions? Okay. So then in the next one, number 7, it says, write the solution that can be read from the simplex tableau right now. So recall, when you read a simplex tableau, you're looking for the columns that are 0s and 1s. So if you didn't already, circle the columns that are 0s and 1s. And those are the solutions that you can read right now. So for instance, x3, the 1 is here. So x3 is equal to 30. So that's one thing I wrote down. And then in the S2 column, the 1 is here. So S2 is equal to 15, which I did not write correctly. S2 is equal to 15, not 1. So then what are the other variables equal to? Yeah, they're all equal to 0. So x1, x2, s1, those are all 0. And then what is z equal to?
6.
Yeah, that little nugget down at the bottom there, z, the 1 is there, so that's what 16 is equal to. So you'll notice you actually have 3 columns of zeros and ones. One column is x3, one column is s2, and the other column is z. In fact, z is always going to be a column. Well, no, it's not always going to be a column of zeros and ones. I take that back. But the bottom part is always going to tell you what z is equal to. So z is equal to 16. Okay, so that's just reading a solution right off of your Tableau.
So that's all you want is x3, s2, and z.
Yeah. Well, I said write the solution, so that includes x1, x2, and s1 all being 0. Yeah, so the columns that you don't read any information from, those variables are equal to 0. But yeah, right there, what I have there, that's what I want. All the solutions that I posted, those are the solutions I want. Okay, so now we begin doing a little bit of work. And number 8, I'm asking you to pivot once about the circled item. So what does it mean to pivot? So what does it mean to pivot that 2? What do I want to turn the 2 into?
A 1.
A 1. And then anything above and below it, I want it to be a 0. So I went ahead and I turned the 2 numbers below it into a 0 first. Oh, and everybody really watch what I did here. I conveniently turned the 2 numbers below it into a 0, which I did. But I never ended up changing the first row here. And this is what you saw online on Pearson. So sometimes they would change the zeros, but then they would leave that number as not a 1. Did you see that online?
Yes.
So what does this really mean? What it really means now is that 2x1 is equal to 48. Now at this point, can I just divide that whole row by 2?
Yeah.
Yeah, so if I divide that by 2, I get my 1. If I divide 48 by 2, I get my 24. But notice you can get it by just looking as well. What we're really saying is that 2 times x1 is equal to 48.
1 times 2 gets you 48.
Right, and so by dividing off the 2 from both sides, we get that x1 is equal to 24, which is what you'd get if you divided that whole row by 2. So even though I didn't finish turning that whole row into a 1, I can still read what the solution is. Just like on Pearson, they would give you this arrangement sometimes, because then you could just divide off the 2 and you'd have the answer 24. So what did we end up with? This is my solution column. So x1 is equal to 24. And then this is another solution column with a 1 and 0. So s2 is equal to negative 16. And then, oh, down here, notice again, they didn't turn that into a 1. But still, you would say 2z is equal to 48. So if you just write down 2z equal to 48, that solves for the final value.
What about the negative 5?
What?
Negative 5.
What about that?
Yeah, doesn't then need to make it positive.
Oh, that's the ultimate goal. But what this says is just pivot once and read what you have so far. So this problem, you're not solving all the way. You're just taking one step and seeing what you have. So again, this 2z equals 48. I mean, if I wanted that to be a 1, again, all I do is divide the whole row by 2. And then it would be a 1 and a 24. And then I'd have my solution for z. Okay, so that's just pivoting once. Okay, but whereas the next problem is a full problem. This next one is a full problem. It says a bakery makes donuts. So immediately we know that's my variables. Sweet rolls is x1 and donuts is x2. And then they go about giving us tons of information. And then you have to figure out how to put it all into a matrix. Would you all like to go through this problem? Oh, and actually, you'll notice this problem says, just set up the initial simplex tableau. So just set it up. You don't even have to solve it. You just have to set it up.
Which is not perfect.
Yeah, so you just set it up. But now, folks, let's remind ourselves. How do we take a word problem and turn it into a matrix? What's the very first thing that you do?
Set your variable.
Exactly, you set your variables. So in this case, and you can even read all the way through, the profit for a batch of sweet rolls and donuts. Again, profit is your objective function, so those must be the variables again. But what we're going to say then is I'm going to start my tableau here. My first variable will be sweet rolls. And oops, my second variable will be donuts. Okay, and then we know we're going to have some slack variables. And then we'll have a z. And then we'll have the numbers at the end. So then what? What do we fill in next? What would be a good place to go now? Yeah, we can talk about the ingredients. I think probably the next best thing to look at is the totals. The fact that they told you that that's the most that you have. That's your less than or equal to. So those are our numbers. So we know that it has to be less than or equal to 600, less than or equal to 740, less than or equal to 760. And now I know what those rows represent, because I know what my columns represent now. Now I want to know what my rows represent. So now I know that this row represents flour, and this row represents eggs, and this row represents sugar. Now I'm one step closer to being able to actually filling in the rest of my information. So for instance, a batch of sweet rolls, so I'm looking at the first column, requires 3 of flour, 1 of eggs, and 2 of sugar. So 3, 1, 2. Whereas then they say a batch of donuts requires 5 flour, 3 eggs, 2 sugar. So 5, 3, 2. And I need to rewrite those. And then who remembers what this whole portion looks like? That's just all the zeros and ones. Because you're going to use this slack variable here, and then nothing else. And then you're going to use this slack variable here, nothing else. And then you use the z goes down there at the bottom. Oh, no, we haven't used z yet. Oh, how many slack variables do I have? I'm sorry. How many slack variables do I have? 3. What's the rule? You have a slack variable for every constraint. So for every constraint or every inequality that you have to have a slack variable. So since I have 3 constraints or inequalities talking about flour, eggs, and sugar, I need 3 slack variables. So now that's what that portion looks like. And then my z, that's my whole last row. This is my z objective function. How do I put in my z at the end? We have to come up with the objective function, and normally objective is profit, so the profit is sweet rolls and donuts. So my z is 138 for sweet rolls and 53 for donuts. So then what do I have to do?
Equal 55.
Oh, sorry, negative. Yeah, I move all my terms to the left, and that gives me the negative coefficients that we know we have to change to positive coefficients. So now what we have is the negative 138, the negative 53, then a whole bunch of zeros until I get to the z position, and that's equal to 0. Because that last equation is negative 138 x1 minus 53 x2 plus 1z equals 0. And that's the last equation that goes in your bottom row. So is that the same thing that I started with? Yeah. Now, just for kicks, oh wait, yeah, that's it. I went ahead and just pivoted once, and I think just by pivoting once, I chose the most negative number, and then I did all the ratios. That was the smallest ratio. After pivoting once, it already gave the solution. So now, knowing that this is our solution, what's our solution? That's a row of zeros and ones, that's a row of zeros and ones, that's a row of zeros and ones. Wait, where's my other? Oh, I didn't finish. Never mind. Forget it. Forget that last part. You didn't have to do it anyway. You just had to set it up. Okay. All right, I see 4 more problems from chapter 4. And that's probably all we have to do since we just finished chapter 5. We probably don't have to do any problems from chapter 5. These last 4 problems you do actually have to solve. So should we do one together? Yeah? So everybody looking at number 10? The initial tableau is given. Use the simplex method to solve. So I'm going to write it down. And everybody, you should write it down as well in your own handwriting. So 3, 2, 4, 1, 0, 0, 15. And 2, 1, 5, 0, 1, 6. 0, 8, and then -1, -4,
Over one.
Okay. So what was the simplex algorithm? What was step 1? Now, keep in mind, here, let's start from the beginning. What's our goal? What's our goal? Yeah, the bottom row is positive. What's our method? Pivot. And the simplex algorithm is how to choose your pivot. So keep in mind, I have a lot of pivots to choose from. I've got 1, 2, 3, 4, 5, 6 different numbers right there that I can choose to pivot around. Because you don't pivot around one of these guys. We're going to pivot around one of these. So which one do you choose? And that's, yeah, step 1 is choose the most negative indicator. So choose most negative indicator. And by indicator, I'm talking about the last row that we're trying to make positive. So that's this number. And then choose smallest quotient or ratio. If you prefer the word ratio, choose the smallest ratio where we're doing right over left. What are we talking about with right over left? We're looking at these numbers and these numbers. So right over left. So this is going to be 18 over 2, which is 9. And then 8 over 1, which is 8. And then 0 over -4, which is 0. And you need to choose the smallest positive ratio. So what's the smallest positive number you see? 8. So now we know that we're looking at this row, we're looking at this column, and so that's our pivot. So step 3, pivot. So that means turn that into a 1. It already is. Create zeros above and below it. So that's what we have to do, is create zeros above and below. Now this is the fun part, right? All these matrix manipulations, bata. Let's get rid of the 2. How do I cancel a positive 2? What would I need to add to a positive 2 to cancel it out?
Row 2,
A negative 2.
negative row 2 plus.
Yeah, exactly. You have to multiply this row times -2, and then add it into the 2, and then that'll cancel out. So I need to cancel a positive 2, I need a -2 right here. And to get a -2 right here, I multiply all the way across by -2. So let me use a different color. So I'm going to multiply that whole row by -2. So 2 times -2 is -4, 1 times -2 is -2, 5 times -2 is -10, 0 times -2 is 0, times -2 times -2 times -2. So now I'm going to add all those into the top row. So 3 minus 1, 2 and -2 is 0, 4 and -10 is -6, 1 and 0 is 1, 0 and -2 is -2, 0 and 0, 18 minus 16 is 2. So there's the top row. The middle row stays the same because we've already pivoted that number and it's already a 1. So now, how do I cancel a -4? Yeah, with a +4. So now I got to multiply all that row by a +4. And this is why I'm doing it in just little numbers with another color, because I'm just going to multiply through. Or I could, I could erase all those purples now. Not that it's very convenient to erase on paper. Okay, so now I'm going to multiply through by 4. So that's going to be times 4 times 4 times 4 times 4 times 4 times 4 times 4. Now those get added into the bottom row. So 8 minus 1 is 7, 4, 4 is 0, 18, 0, 4, 1, and 32. Okay, so did I successfully pivot? Yeah. And is the bottom row positive? Yeah, that means we're done. So if bottom is positive, you're done. If not, repeat. And you just go back to the beginning and start over. Okay, but in our case, we're done. So we can read these solutions. So what is that? We need to go back now and fill in all of our variables. What is that, number 10? So that's x1, x2, x3, s1, s2, z, and a number. So one solution is that x2 is equal to 8, And S1 is equal to 2, and Z is equal to 32. And what did we just find out anyway? Theoretically, this objective function that we had, the objective function, was asking us to maximize that objective function. So if you look here, that's negative 1x1 minus 4x2 minus 2x3 plus 1z equals 0. If I solve this problem for z, that means z is equal to 1x1 plus 4x2 plus 2x3. And so what we just did was we just maximized the value of z. And what is the biggest value of z? 32. So the largest value that z can take on is 32, given the constraints in the first two equations. Okay, well, that was a pivot problem. I don't think we have to do number 11 because it's the same and one pivot will do the trick. So number 11 is just like that. Does anyone have a particular question about that? Okay. Let's take a look at the last two. The last page is on duality theory. And you'll notice that for number 12, I wrote just set it up. So you do not actually have to solve number 12 all the way through. I just want you to set it up. So what does that mean? Let me erase and give myself some more space here. Did everyone write down all these formulas? I'm assuming you did. I'm assuming you did.
So on the test, you would just have to set it up, or we have to?
Yeah, on the test, all you have to do is set it up. Okay. So let's look at number 12. This is just set up. So they're telling us they want us to minimize the value of W, which is 6x1 plus 3x2, subject to those constraints. I can write them all down. The key is that you first take your minimization problem and write it down as matrix A. So what is matrix A? Okay, we're almost done. Matrix A is you just take the coefficients from the constraints just as they are. So that would be matrix 3, 2, 30, and then 2, 5, 40. And then the bottom row is just the coefficients from Z with a 0 at the end. So notice how this is different. In the past, in doing the simplex algorithm, we kept on getting negatives over here that we want to turn positive. Not so with doing a duality problem. First, you just take all the coefficients as they are, and then what do? You take the transpose. And the transpose means turn each row into a column. So my row, 3, 2, 30, becomes a column, 3, 2, 30. And my row, 2, 5, 40, becomes a column, 2, 5, 40. And my row, 6, 3, 0, becomes a column, 6, 3, 0. So now that's my A transpose. And now this represents a maximization problem. So whereas this was representing a minimization problem, this is now representing a maximization problem that you can solve with the simplex method. So now we have to put everything back in again. We have to say, well, these are my constraints. So that's less than. And this is my objective function. So we want to write it down. This is what I mean by setup. Let's just write it down. So now this is my, they already used the variable x, so I'm going to use the variable y. y1, y2, and a number. So this means one of my constraints is 3y1 plus 2y2 is less than or equal to 6. My other constraint is 2y1 plus 5y2 is less than or equal to 3. And then my objective function is z equals 30y1 plus 40y2. And this is what we want to maximize.
That might be it.
Well, what did I write down? Yeah, you certainly don't have to solve the whole thing. But now at this point, you can still put this in the initial simplex tableau and then not solve it. Yeah. Or is that far enough? Is that enough? Yeah. You guys want me to give you full credit for just setting it up like that? Yeah. Okay, then that's as far as you have to take it. Because the next problem, you're actually going to solve all the way through. Okay, so this one says use the simplex method to solve this problem. So this is the minimization problem they give you, and now I want you to go ahead and solve the whole thing. So I'm going to finish solving this one, right? Because we're already almost there, At this point, we just put this in an initial simplex tableau. So again, remember, you have as many slack variables as you have constraints, so it's going to be S to Z and then a number. And so my first row is 3, 2, 1 slack variable, and then nothing is less than 6. My next constraint is 2, 5, not that slack variable, this slack variable, and nothing. And then my objective function, again, moving those to the left, would be negative 30, negative 40, 0, 0, 1, and 0. Okay, well, class is almost over. We're not going to solve a whole nother one of these. But now, what would you do? You would pivot, and you'd find the solution. Now, keep in mind, can everybody just look up here at this solution? So this problem number 13, I did solve it. I got all the way down. Is my bottom row all positive? Yes. Yes. So, what to notice here? Once you solve the maximization problem, you know that the maximum value of Z is 40, which simultaneously means the minimum value of W is 40. So that value applies directly to the minimization problem. But instead of solving for these variables, you just look at the bottom 2 slack variables. And those bottom 2 slack variables are the values of the y1 and the y2 from your objective function. Okay. That's probably it. Everybody, I'm sure, is ready to go. It's been a nice, long day.
Yes.
Anyone want to stay for another hour? No. I had the grandest intentions of letting you leave early. But... Hey, you're leaving a minute early. Nice. That's something, right? Hey, who wants the extra practice test? It's very good.